I'm very, very grateful to the organizers for having me at this meeting. It has been extremely interesting. And before I start my talk, I think I should start with a couple of warnings. First, as Friederike pointed out, I have come to look at generalized Langevin equations from a different point of view, I think, than the one that you're used to. And it is because I am interested in trying to include nuclear quantum effects, and I mean in particular in time-dependent properties, such as time correlation functions. This is not something that I think we have heard a lot about during this particular talk. And the second warning is that a little bit because of this different point of view, and a little bit because this is the last talk of a very interesting and very intense workshop, I have indulged in some silliness. I hope you will forgive me. This is in part in my nature and in part because I think it's useful to end in a relaxed tone. More seriously, the work that I am going to describe is part of a collaborative effort that has had many different friends joining in the game, all the way back to when I was still in Rome with Giovanni Ciccotti, more recently with Rodolphe Villemieux, and then even more recently, and this is really the team whose efforts I am going to describe for you today, with Simon Huppert and Thomas Play, Fabio Finocchi and Philippe Depont at UPMC in Paris. So time correlation functions, right? So let's start from something that I think we are all quite comfortable with, and this is a definition for a classical time correlation function of two observables, A and B. Now I have written it here as an integral over the phase space of the system of a weight, a probabilistic weight, which is the probability density for the system. Let's think NVT situations, and so thermal equilibrium e to the minus beta h, essentially. And A and B are two general observables, for example, velocities, if I'm interested in looking at diffusions, or if by Fourier transform, I want to look at infrared spectra for my system. And as you can see, the structure here is that I have to evaluate my operator A at the initial point of the trajectory, or at the initial point in phase space. That is the one that corresponds to this P and Q pair here and this integral here. But then I have to propagate the dynamics of the system, in this case, classical dynamics up to a time t, measure the function B, and then that gives me my time correlation function. Now, if I went a bit crazy and decided to compute this time correlation function through some kind of Monte Carlo scheme, what I just described is more or less what I would do. I would sample initial conditions according to the probability density for the system. From each sampled initial condition, I would propagate a classical trajectory, measure A, measure B, and then obtain the time correlation function as the sum over all the realizations of this product A of 0 and B of t over my ensemble of trajectories. Now, this is not the way we do it. Usually what we do is we propagate a trajectory whose dynamics is, preserves stationarity of the probability density, and then I obtain the time correlation function by, looking at products shifted in times along this trajectory, or using the Wiener-Kinshine theorem through Fourier transform. But if I decided to do this through the Monte Carlo procedure that I just described, this wouldn't be, too much of a problem, because in classical systems, I have well-established methods to sample the thermal Boltzmann density for my system, and integrating the evolution equations is something that we all know how to do as simulators. So this is something that we know how to deal with. And of course, there can be all sorts of complications. We've heard some of them in this workshop, but the basic strategy is very clear. Now, if I try to have a look at the analogous problem, but in quantum dynamics, then my life becomes a bit more complicated. Not so much if I think about the thermal weight for my system. This here is the quantum Boltzmann operator, so e to the minus beta h hat now. And then the structure of this average that defines my quantum correlation function is in some sense similar to the one that I just described. In classical mechanics, I had an integral over dp dq, so a sum over all the possible states of my system. In quantum mechanics, I have a trace operation that is the analogous of that. I have my probabilistic weight rho hat. I have an observable A measured at time 0, and then I have an observable B that I want to measure at time t. And now this time t corresponds to an evolution of propagation in time that is the full quantum propagation for the system. And so here it's written in Heisenberg propagation, but you know, any representation will do. Now, if I try to think about algorithms, numerical algorithms to actually perform these operations, the calculation, the sampling of the quantum thermal density, this is not really a challenge nowadays. We have well-established methods, for example, in the framework of Feynman path integrals, to actually do this. And these methods work largely because we can benefit from isomorphisms that in the path integral language take the quantum Boltzmann operator and transform it from being an operator in an abstract space into being a function of coordinates of the system that looks a lot like a classical probability distribution function. And then we can transfer all the beautiful techniques that we have for sampling classical probability densities to the quantum domain. The calculation of observables per se, when they are not too difficult, so for example, relatively simple functions of coordinates or momenta of the system, that is not a problem. What is really a killer is trying to solve the full time-dependent Schrödinger equation for my system, so determine the exact quantum density, the quantum propagation. And if I think about the situation in terms of numerical algorithms, then I feel like celebrating the fact that Dante Alighieri died 700 years ago this year, and use his journey to try to illustrate the situation. Except Dante went from hell to heaven. We are going to go the other way around in this tour of approximate methods for obtaining quantum mechanical dynamical properties. Now, the reason why we're going to go from heaven to hell is because heaven is the domain of exact methods for solving real-time propagation. And this, at the moment, seems like an unattainable goal because all available exact methods scale exponentially with the number of degrees of freedom in the system. If we move, one step closer to humanity, if you want, and we try to go to purgatory, then we find a set of methods that are typically called semi-classical or linearized methods that work starting from relatively well-defined approximations of the full quantum propagator. They differ depending on the type of representation that I use for propagators. So, Heisenberg or path integrals, for example. But they all share the fact that at the end of the day, they require to combine methods for exact sampling of the quantum thermal density with propagation of classical trajectories. Now, this is something that we feel quite confident about because I mentioned that we have methods for these exact sampling of the quantum thermal density, and because classical trajectories are something that we can manage quite well. The drawbacks of these methods is that numerically they remain quite expensive, which means that if I try to scale up the size of the system or the time lengths for which I need to follow the correlations, then I am rapidly in trouble. The fact that we substitute full quantum dynamics with classical trajectories, not one, but ensembles, I will say a bit more about that later, still means that we don't have fully quantum coherence dynamical effects. And there is another drawback of this class of methods, and that is that because I am now propagating using Newtonian or Hamiltonian dynamics a quantum object, I am not really conserving the quantum thermal probability. And this has all sorts of, this causes all sorts of pathologies, some of which we may describe a bit later. So if I want to tackle even larger systems or try to move one step closer to realistic simulations, then I have to make the transition to hell. And here I find a whole family of different methods, some of which I have mentioned here: ring polymers, molecular dynamics, centroid molecular dynamics, the quantum thermal bath methods, that all share the following basic philosophy. They try to use sampling dynamics for the quantum thermal density. So the sampling dynamical systems that we can use, that are legal if I want to look at static properties, and then use them also to compute time-dependent properties. So my sampling trajectory now is given, and this is usually arbitrary, a dynamical meaning, and the time along this sampling trajectory is no longer the analogous of a Monte Carlo time, but is really associated to the physical Newtonian time for my system. The drawback here is that formally there are no exact ways or no clear ways or clean ways to actually derive any of these methods from exact quantum propagation schemes, but they have the advantage that they conserve the quantum thermal density along the dynamics by construction, because the dynamic that I am using is a sampler for the density. Either the exact quantum thermal density or approximations that are considered quite good to the quantum thermal density. The methods that are developed have the property of becoming the classical methods in the classical limit, and they all are exact if I look at harmonic systems. Their main advantage is that they are cheap methods. So now let me start by spending a bit of time in purgatory and telling you about linearized approximations for time correlation functions. The main ingredient, or one of the most useful ingredients in this domain, is the Wigner representation of quantum mechanics. Now, this is perhaps a slightly unfamiliar framework that was originally proposed by Wigner in the 30s of the 1900s. And the reason why this is an interesting object for us is because it's a way to write quantum expectation values in a form that has striking similarities to classical averages. So if I look now for a moment at the time-independent average of a quantum operator A, this can be represented exactly using the Wigner representation as an integral over coordinates and momentum for my system of something that is called the Wigner representation of the operator A times something that is called the Wigner representation of the quantum thermal density. Now, Wigner representations are transformations that take me from operators to functions in Q and P, and they are more or less all defined as described here for the Wigner thermal density as Fourier transforms of off-diagonal elements of the operator that I'm interested in. So here is the thermal density. I just consider a point Q. I symmetrically shift by an amount delta over 2 with respect to this position Q. And then I take the Fourier transform with respect to the delta variable to obtain my Wigner thermal density. Now, this representation of quantum averages for static properties is not used or particularly useful because the alternative methods that I mentioned before, and in particular Feynman path integrals, are way more efficient than these. But they are at the core of these semi-classical approximations for time correlation functions. And this is because if I take a semi-classical limit of the exact Wigner representation of a quantum time correlation, then what I obtain is something that looks like this. And this is, as you see now, an integral over Q and P, very much like in the classical case, of something that I am going to interpret in a moment as a probability density for my system, and that sets initial conditions, times the Wigner transform of the operator B, computed at positions Q and momenta T that are obtained by propagating classical dynamics from the initial conditions Q and P. This is the semi-classical form of the time correlation function that I am going to look at for a moment. Now, the reason why this is interesting is because if I play a bit fast and loose with this Wigner representation of the product of the thermal density and the operator at time 0, and I approximate it as the product of the Wigner transform of the thermal density times the Wigner transform of the operator at time 0, this is an approximation, but we don't need to dwell on that at the moment, then a Monte Carlo calculation of this integral here can go very much along the lines that we discussed in the first slide, because I can imagine sampling initial conditions from the Wigner transform of the quantum thermal density. And then from each sampled initial condition, I can propagate a classical trajectory, measure the Wigner transform of A at QP, measure the Wigner transform of B at QT PT, and then average the overall different over a set of different trajectories to obtain the time correlation function. Now, the first thing that I should say about this is that classical evolution of the dynamics does not conserve the Wigner representation of the thermal density. This is the pathology that we mentioned also before. But the integration of the evolution equations is easy, Newton. The form of Wigner transform of simple or operators that only depend on Q or only depend on P is the operator, the function at Q and P. So the Wigner transform of Q hat is Q, and the Wigner transformation of P hat is P, for example. And so measuring these operators is easy. So we are, where we said we would be when dwelling in purgatory. Now, the difficulty and the incorrect statement or imprecise statement that I just made had to do with my intention of sampling initial conditions from the Wigner thermal density. Why? Because the Wigner thermal density is defined as we discussed before, and it has some nice properties. For example, if I take W of Q and P and I integrate over Q, I'm going to get the exact quantum probability in the P representation, and vice versa. If I integrate over P, I am going to get the exact quantum probability in the Q representation. But this function here, in general, is not a positive definite function, and so it cannot be immediately interpreted as a probability. Okay, then that's a problem, but maybe not such a huge problem in the sense that I can probably isolate a positive definite and normalizable part, and then somehow account for the sign in some kind of reweighting. The problem is that computing this Fourier transform for highly dimensional systems here becomes a numerical nightmare. So if I try to compute W of Q and P by brute force, then I am faced with a rapidly oscillating function that it's very, very difficult to get numerically. And this is the reason why exact sampling of the Wigner thermal density is not what people typically do. People typically propose approximate methods. Of course, all these approximations have as a target numerical efficiency, and so typically they are numerical efficient. But the problems is that they are often, in fact, almost always based on harmonic approximations of the potentials, which then can be questioned for general systems, and that they tend to lose some of the properties that are intrinsic quantum properties of the system. For example, the momenta and positions of the system are typically uncorrelated in this type of system of approximations. And furthermore, they only give you the positive part, contribution to the Wigner density. They very rarely are able to account for negative aspects of this function, which can modulate the behavior of the system and of the observables. So a while ago, and this is something that we did first with Giovanni, then with Rodolphe, and then again with Simon and the others, we tried to come up with a way to approximate this Wigner density that somehow could mitigate some of these pathologies. And this is what we did. I mean, we basically used this notion of an Edgeworth, or if you want, generalized cumulant expansion for the Wigner density. And the result of this, of a bunch of manipulations that I don't want to describe in detail, but I'm happy to tell you more about if you're curious, is that we are able to rewrite the Wigner density as the product of two terms that have the aspect of a standard probability density, with a couple of caveats that I will describe in the next slide, times a series of terms that can have different sign and therefore, contribute to changes in sign. But the part that is squared in red here, this can be interpreted in the standard term as a probability density for my system. It's a probability density in P and in Q. So it's a joint probability density. You see that interestingly, there is no separation of variables, right? So this is able to maintain some correlation between Q and P. Now, I've introduced here a bunch of objects, U, K2, and all these averages with respect to this mysterious probability rho C that need to be discussed and defined. The first thing to say is that this rho C is a conditional probability for the delta variable that appeared in the Wigner transform for any given value of the coordinate. The good news is that this thing here can be expressed using, for example, path integrals like a classical probability density, which means that anything that is an average over rho C is something that I can compute as using classical methods. But this also tells you, by looking at the definition of kappa 2, for example, which is just the second order cumulant of this conditional distribution here, that some quantities appearing in my probability density here are not known analytically. For general systems, this is something that I can compute, but it's not something for which I can give you a nice analytical expression. The same thing is true for this function u of q, which again can be obtained as an average over this rho c, but it's an average. So the first odd, if you want, or nasty property of my definition of the Wigner, of the positive part of the Wigner density, is that I have to express it in terms of quantities that I have to estimate through a numerical procedure. So I have anticipated part of what I wanted to say here. P of Q and P here has the good property that in the classical limit, this goes to the Boltzmann distribution. When we are away from the Boltzmann, from the classical limit, it seems to preserve some of the characteristics of the quantum system that I described before. For example, correlation between momenta and positions. But there is this nasty aspect that I have to do more than what I usually do to sample it, because I have unknown functions, in particular u and kappa 2 in its definition. Now, there are techniques that have been developed to sample noisy probability distribution. Typically, they come from the world of Monte Carlo. And this is the way in which we started looking at this problem and starting finding ways to sample the probability. More recently, we tried to see if we could come up with a Langevin type dynamics that would do the trick for us. And the answer is yes, you can. By using the Fokker-Planck equation, you can obtain a Langevin system that will sample this probability density. But now the structure of this Langevin dynamics that we call the Wigner Langevin dynamics or the wild dynamics, for reasons that are probably obvious by just looking at the structure, is that now that the force term here depends both on Q and P, and that the friction depends on Q. The good news is that R of T is a white noise. So this is the only standard Langevin-like feature of this particular equation. Now, this thing here can be used to sample to sample the distribution. It can be used to sample static properties. And we have done that with I would say, good success, but for small model systems. Because if you now look a bit more at the structure of the force and at the structure of this friction, you realize that the force not only couples Q and P in very nasty ways. For example, here there is this P squared term times the logarithmic derivative of kappa 2, but you also realize that this force here contains terms that are estimated numerically, which means that you have to deal with a propagation in which you have noisy forces. And this is very, very difficult to keep stable, if at least, and that's maybe one of the questions that I have for this audience. And so it's very expensive to actually integrate these dynamics. But we want to go one step beyond, and so, you know, in some sense, move deeper into hell now, because we don't want to use the Langevin trajectory that we obtain by solving these wild dynamics only to compute static properties, but because we now have a time evolution that conserves our approximation for the Wigner representation of the thermal quantum density, we want to see if we can actually use this dynamics to compute time correlation functions. Now, in addition to the fact that the Wigner representation that we are using is stationary under these dynamics, you can also show that our Langevin equation reduces to the classical Langevin equation when we go to the classical limit, and that if the system is harmonic, what we are proposing is exact sampling of the quantum Langevin equation for this system. Of course, I don't have a reason to imagine that this dynamics here is any reasonable approximation to the full quantum evolution for my system. Does it work? Well, we tested it in a system that we have been looking on and off for different gaming purposes over the years, and this is a model system for Fermi resonances in CO2. It doesn't particularly matter to understand the structure of the system. The only thing that it's interesting for us is that if I look at the high frequency region of my vibrational spectrum, I see two peaks here. This is the manifestation of a Fermi resonance, and that the amount of splitting between these two peaks, so between the position of this maximum and the position of this maximum here, is known to depend on temperature based on, for example, quantum perturbation theory treatment of the system. Now, if we run the wild dynamics for the system and we compute the velocity-velocity autocorrelation function for the system, and we take the Fourier transform of this velocity-velocity autocorrelation function, these are the spectra that we obtain for different temperatures. And because this system is essentially a three-dimensional system, two dimensions are really interesting, we can also provide you with exact solutions. And if I compare the exact quantum spectrum with the one that I obtain with wild, what I find is very, very good agreement between the exact and our result. We don't know why, but this is interesting. And it's tempting also because, and this is my second silly moment, if you haven't seen Coco, the movie by Disney and Pixar, I highly recommend it. And there is a dog called Dante for very good reasons in that movie, who here is tempted by a bone in the same way in which we are tempted by these dynamics, because this form of propagation seems to salvage quantum properties that alternative methods based on this idea that you just propagate class dynamics that somehow preserve the quantum thermal density don't seem to capture. In particular, here I am showing what happens to the distance between these two peaks as we lower the temperature of the system. And what you see here is the quantum result that saturates at some point due to 0-point energy effects. And this behavior is captured by the Wigner dynamics, whereas other methods behave classically. Now, this is interesting because both my dynamics here and what the other dynamics do washes away coherence. The quantum coherence effects are not here, right? And so people always said that the reason why this type of effects could not be captured by that type of evolutions was because by construction, coherence wasn't accounted for. But the wild dynamics doesn't have coherence and still manages to capture this type of effects. So this prompted us to analyze the situation a bit better, and we understood that there are a lot of this, some behaviors of this type, in particular, when you look at things like the behavior of the Fermi diode as a function of temperature, or the intensity of harmonic features in vibrational spectra as a function of temperature, so overtones or combination bands, is not so much the quantum coherence that you have to preserve, but it is this correlation between positions and momenta in the initial sampling. Now, having seen using the wild dynamics, we decided to look at alternative ways that are much, much cheaper computationally. And this took us to looking at these so-called quantum thermal bath methods. Now, this is a Langevin force. This is a standard Langevin equation for the system. This is just the force. This is the velocity-dependent term here with a constant friction term. And the only difference between this guy and a standard classical Langevin equation is that the spectrum of the force in the force-force correlation function in Fourier space is not constant, but has the shape of the distribution of frequencies for a harmonic oscillator at temperature T. This equation here was invented independently by different people. And again, there is no way that I am aware of to derive it from exact quantum dynamics or exact quantum statistical mechanics. It also has, but it has several interesting features because we are using this quantum oscillator thermal pumping of energy, if you want, in the system. 0-point effects are accounted for by this Langevin equation. 0-point energy effects are accounted for. Again, this is a dynamics that for a harmonic oscillator is essentially exact. It has the huge numerical advantage of being incredibly cheap, but it suffers from a pathology. And the pathology is that I am trying to combine quantum statistics with classical evolution. The classical evolution will try to take me towards equipartition. And so in particular, same amount of energy in high frequency modes and low frequency modes. the quantum would like me to keep into account 0-point energy for these different modes, but classical doesn't like that. So classical will try to transfer energy from high frequency to low frequency modes. And this is the so-called 0-point energy leakage pathology for this type of dynamics. And it can have rather severe effects. For example, I mean, if I look at ice at 150K, and I look at the G of R of the system, here, this is the classical result. In black here is the path integral result, that it's our exact quantum reference. And if I just propagate the quantum thermal bath Langevin dynamics and accumulate the average of this quantity, the longer I propagate, the worse my life becomes. And in particular, ice melts in about 750 picoseconds, as shown by this curve here. So, and this is mostly Simon Huppert came up with an idea to try to mitigate this effect. And he realized that one of the ways in which this 0-point energy leakage manifests itself in the system is that the quantum fluctuation dissipation theorem is violated. And so he came up with a scheme to actually adapt the friction coefficients in the quantum thermal bath Langevin equations in such a way to basically compensate dynamically for this. Now, this has a slight additional numerical overhead compared to standard quantum thermal bath, but it reduces very much this pathology. And in fact, if I now show you in a different form, I apologize, but the same curves that I have shown you here, the AD-QTB result matches for infinite propagation times, if you want, the exact QTB, the exact path integral molecular dynamics reference. Now, as before, we now have a trajectory that shows stationarity with respect to whatever probability density is sampled by my quantum thermal bath. So again, I can give in to the temptation of looking at time-dependent properties. And again, for example, at the IR spectrum now of my ice system. And here I find the same kind of slightly surprising thing that I found for wild dynamics and the Fermi splitting. Because if I look at the spectrum and I compare with other available methods, what I find is that if I look at the low frequency modes, symmetric stretching, bending, asymmetric stretching, more or less in those regions, the behavior of the correlation function computed using the adaptive quantum thermal bath, and for example, the behavior of the correlation function computed by path integral methods are quite similar. But if I now go to the anharmonic regions of the spectrum, then again, I find that for reasons that we do not understand too well, the adaptive quantum thermal bath seems to do better. And I can say this because I have benchmark results that substantiate this claim, does better than, for example, the ring polymer molecular dynamics. So this is something that we were quite intrigued by. Now I realized that I took you through a very quick tour of uses of generalized Langevin equations to try to approximate time-dependent quantum properties. I think that one of the reasons why it was so interesting for me to listen to you all and to then maybe share with you these different types of adventures is because we have questions that are obvious and that are open questions, and it would be great to see if we can share some thoughts about them. The first one has to do with the integration of noisy Langevin equations. Are there ways to actually mitigate the numerical pathologies associated with that? Then there is this whole other thing here that has to do with the wild, and in particular with the adaptive quantum thermal bath, which is, we know what equation we are solving, but do we really know if we are sampling a good or a bad approximation of the exact quantum density? And I don't think that anybody has an answer to that question. We know that we are stationary with respect to some distribution, but we don't know what that distribution is. So do we have a way to try to investigate this problem? Now, these are my two main questions. But if I have to come up with some conclusions for this tour, I mean, it's interesting to see how Langevin dynamics can be used also in the context of quantum dynamical calculations. They can lead, for example, through the wild scheme to accurate but expensive sampling of good approximations of the Wigner thermal density here, using even more brutal approximations or uncontrolled approximations to the sampling of the quantum thermal density, as we do in the quantum thermal bath or in the adaptive quantum thermal bath, we seem to come up with other schemes that enable us at a very, very low computational cost to have reasonably good approximations for quantum time-dependent properties. And trying to investigate why we get this good agreement is, I think, an interesting theoretical question. With that, thank you very much for staying with me, and I'd be happy to take some questions.